In today's class, we'll see how to find the pseudo inverse. See, normally, if A is a square matrix, then we know that if A inverse exists, A into A inverse equal to A inverse into A equal to an identity matrix. I mean, you multiply a left side or right side with A inverse of A, it doesn't matter, right? Then if you then one is called a left inverse, another is called a right inverse. And in this case, if A is a square matrix and if A inverse exists, then a left inverse equal to right inverse, right? And in fact, that equal to the A inverse. But that's not the case when A is not a square matrix. A is a m by n matrix. Then left inverse is not equal to right inverse, and so on. One may exist, other may not exist, and so on. So we have to decide whether it's a left inverse or a right inverse, and so on. That's what I call a pseudo inverse. That inverse is what we call the pseudo inverse. All the work, there are many pseudo inverses, but we mainly discuss about more Penrose inverse. This we call it in general a pseudo inverse, right? So in linear algebra, we call that, and it's denoted by a dagger. Some they call it a plus, whatever. Okay, we'll call it a plus, right? It's known as a generalization. It's a general inverse of a matrix. Right? Every time the term general inverse, we use it as a synonym for a pseudo inverse. So we'll stick on to pseudo inverse, right? Where it's used. Inverse is basically used, we have seen in earlier classes. Inverse is basically used to solve a system of linear equations, right? Here also we solve a pseudo inverse is used to solve a system of linear equations in a best fit sense, right? A system may not have a unique solution, means it have either a no solution or infinitely many solutions. If it has no solution, what is the approximate best solution? If it has many solutions, then which one norm is minimum, right? All these examples we'll see later on a couple of slides, right? And how do you find a pseudo inverse? The general method is by singular value decomposition. But anyhow, we'll see if it has a full rank, how to find the inverse, right? If right, anyhow, the general technique is a singular value decomposition. That's one. What is an identity matrix? You know, identity matrix is a square matrix with all the diagonal elements equal to 1, non-diagonal elements equal to 0, right? And you know, a matrix defines a linear transformation. When you apply an identity matrix or identity transformation, the space doesn't change. No, it goes into the same space, right? Okay. If A is a m by n matrix, and if the system has a unique solution, then the pseudo inverse coincides with the regular standard inverse. Then A inverse equal to A plus. The problem is if it has infinitely many solutions or if it has no solution, right? In the case if it has no solution, the pseudo inverse is obtained. Uh, we take a minimum Euclidean norm. That's a we'll see. That's the one we choose as the best solution, right? Now, if rank equal to number of columns, we'll say it's a full rank. If rank equal number of rows, we'll say it's a full row rank. Number of columns, it's a full column rank, right? If A equal to number of rows, if the rank of A equal to number of rows, then the pseudo inverse is defined like this: A plus equal to A transpose A transpose whole inverse. This is called a left inverse. And if rank of A is equal to number of columns, then A plus equal to A transpose A whole inverse into A transpose. This is called a right inverse, right? So it's a left inverse or a right inverse. We need to choose, right? Now, if rank of A is neither equal to number of rows, number of columns, then we'll see. We use, anyhow, we have a generic technique called a singular value decomposition. And with the help of singular value decomposition, we'll find the pseudo inverse, right? So, in a nutshell, this is what we want. If A is n by n matrix and m is less than n, right? And rank of A is equal to number of columns, then A plus, the left inverse is given by A plus equal to A transpose into A transpose whole inverse. If m is greater than n and the rank of A is equal to the number of columns there, then A plus equal to A transpose A whole inverse A transpose, right? Right. If it doesn't have a full rank, then we use a singular value decomposition. Right. We'll see. We know by a singular value decomposition, A can be decomposed as U sigma V transpose. Right. We are more interested in this sigma, where sigma is the diagonal matrix with the diagonal elements as singular values over there. We arrange them in an order. Right. Then A plus is given by mean inverse. You take inverse on both sides. Then it is V sigma plus U transpose. Where how to write this sigma plus? Sigma plus is a reciprocals of that singular values. 1 by sigma 1, 1 by sigma 2, 1 by sigma 3, and so on, 1 by sigma n. That's how we compose the A plus. See, we, once you have a singular value decomposition, A equal to U sigma V transpose, then U you have in your hand, V you have in your hand. Only thing is you have to compute that sigma plus. Sigma plus is nothing but the reciprocals of those singular values, right? Here it is. A plus is given by V sigma plus U transpose. Right. Let's do a couple of problems. Then find the pseudo inverse of A. Right. This is a 2 by 4 matrix, and we see the rank of A is 2, and it has a number of columns. So it's a right inverse, what we say. I'm sorry, it's a right inverse. So A plus equal to A transpose whole inverse. Now, once A is known, we calculate A transpose, which is a symmetric matrix and a square matrix. Inverse do exist, right? So A transpose is this. A transpose whole inverse is 1 by determinant of A into adjoint of A. And from earlier classes, you know how to find the inverse. This is the A inverse. Then A plus equal to A transpose, here is A transpose, then A transpose whole inverse, A transpose whole inverse, right? Then you multiply all these three things, right? This being a constant taken out, and this is the multiplication of these two matrices is this, and finally divided by 2. 32 is this guy. So pseudo inverse here is this, right? Now, second example. This is a 3 by 2 matrix, and rank of A is 2 and is equal to number of columns. So we have left inverse here. So A plus equal to A transpose A whole inverse into A transpose. Now A transpose A is this, which is a symmetric matrix, and the inverse do exist. This is how we find the inverse, right? 1 by 35 into 6 minus 7 and 14. Right? Once you have A transpose A whole inverse, then A plus equal to this A transpose A whole inverse into A transpose, right? Right. This is what the pseudo inverse. Now, A equal to 1, 2, 2, 4. Rank of A equal to 1. So, it's not equal to number of rows, it's not equal to number of columns. So, we have to get A plus by a singular value decomposition. We know this last class we have seen how to find the decomposition of a general matrix, right? We know A is U sigma V transpose. So A plus equal to V sigma plus U transpose, right? So you get the SVD by calculating the left singular vectors, right singular vectors, get A transpose, get A transpose A, get their eigenvalues, get their eigenvectors, right? A transpose and A transpose A, its eigenvalues are 5 and 5. So, they go as 25 and 25, they go, 5 and 5, they go, their square roots, root 5 and root 5 will go as here it's wrong, it should be root 5 here. So root 5 and root 5 will be the diagonal elements, right? So this is my U and this is my sigma, this is my V, and once you have a V, we get a V transpose, but we need a U transpose here. So A plus is V, this is the V, and sigma plus, and this is the sigma plus. Right, the singular values are 5 and 5, meaning the eigenvalues are 25 and 25, right? So sigma plus is 1 by 5. I think we need to check it out here. Please check it out. Right? So sigma plus is 1 by 5 reciprocals of those singular values. And this is a V transpose. You multiply all these three, then it is a 1 by 25, 2 by 25, 2 by 25, and a 4 by 25. That's how we find the pseudo inverse, right? And in the next class, we'll see how to solve the system of linear equations with the help of a pseudo inverse. Basically, it's used to solve a system of linear equations over there, right?